Hi, everyone. I'm Dean Wampler from Domino Data Lab, where I'm a principal software engineer. Previously, I was at Anyscale, the company behind Ray. And so that's what I'm going to talk about today, is how Ray is being used in some popular natural language processing libraries, why it's being used, and what general problems Ray solves. So a little bit about Domino, just shameless plug. It's a enterprise class system for managing the artifacts, the work of data science teams, everything from research to deploying and monitoring models and so forth. So do check us out, dominodatalab.com. All right, well, let me first start with why Ray. What's the big deal here? Well, if you look at this chart at the top right, it's basically plotting on a log scale the amount of petaflops required to train some of these models that have been state of the art over the last 8 or so years. And roughly it's been growing at a factor of 32 times every 2 years. The reason 2 years is chosen is because the famous Moore's law is basically 2x or so every 2 years. So we're obviously greatly outstripping the ability of hardware to keep up with the models that we're building. As I think everyone in this audience knows, natural language processing is the world's biggest neural network models, at least that are publicly known about, with billions of parameters. So this is a real problem. The only way that we can really address this problem is to make it possible to scale in a distributed way, to leverage clusters of computers and hopefully reduce the time that it takes to get from beginning to end. The other big trend on the bottom is the rapid growth of Python over the last decade or so, driven by the fact that it's become the most popular language for data science. And that means that when you put these two factors together, we really need a easy-to-use tool oriented towards Python, not necessarily restricted to Python, but a tool that lets us do distributed computing at scale. Ray emerged out of the University of California at Berkeley, out of the RISE lab, which is a research lab mostly around reinforcement learning and distributed computing. And the problem that these researchers ran into was they needed to be able to do this kind of distributed computing. They needed a framework that was very flexible, not just for sort of, big wads of data that you might use a database for, or Spark, something like that. But they were doing things like reinforcement learning, where you have to run like simulators, game engines, run a lot of them in parallel, as well as train neural network models and so forth. So they needed a very flexible compute system for distributed computing. But they also wanted it to be as easy as possible for people to use who didn't want to have to think about distributed computing. They just wanted to be able to very concisely express what computation should be done that way, and then let the back-end system make reasonable default choices about how that works. And I think this is really what they've succeeded at doing. This is what got me interested in Ray from the beginning. And we'll see in the next few slides how concise this API is. There's really only like 7 API calls at the core of Ray, other than things like configuration kind of calls. We'll look at 6 of them very quickly, and you'll get a sense for how easy it is to use Ray. Even though most of the time when you're actually working with toolkits built on Ray, you may not even know that you're using Ray necessarily. It's just kind of doing its work under the hood, so to speak. So anyway, if you want to find out more about Ray, go to ray.io, and you can get information about it, Ray, and so forth, and also other people who are using it. All right, so let's very quickly see how you could actually scale Python applications over a cluster. I should say that when Ray 1.0 comes out, I think in a month or so, it's actually going to have a Java API as well. But mostly it's been a Python API. So something we all know how to do in Python is write functions. So here I've got a couple of sort of worker functions, one of which will make some sort of NumPy array, and the next one which will add 2 arrays together. Not terribly exciting, but of course the purpose is to see what Ray can do to make this parallelized and distributed over a cluster, right? So to turn these functions into what they call tasks in Ray, you add this decorator at ray.remote, and now these things will become Ray tasks that can be distributed over a cluster and run asynchronously. And for completeness, there's a little code on the right-hand side that you would have to add to make this a little bit more of a complete example. Import Ray, import NumPy, and then fill in the ellipses for arguments that you might pass to Ray and Knit, although the default of no arguments is what you would use on a laptop, for example. And then somehow fill in the details for make array to construct, maybe a billion element array or something, whatever you want to do. And then the way that you use it is something like this. Let's call make array twice to create two arrays. And notice that we have this .remote call that you actually use to invoke a task. Now, Python's pretty malleable. We could instrument the code so that you don't have to use this .remote function, but it's nice documentation when you see this in an application that's using Ray. You know right off the bat that it's calling to Ray. And also the thing that it returns isn't an array in this case. It's actually a reference to some asynchronous computation that's happening in your cluster. So it looks something like the diagram on the right. These two calls to make array are going to return these two references. And then we're going to pass those to Ray, to this add arrays method, or function rather, and that's going to return a reference to the summed array. And then we can call ray.get to actually retrieve that value to get the array. Now, there are a couple of things that have gone on here that make this really a nice tool to use. I've got these computations that have dependencies, so I need to run them in the right order. But Ray handles the scheduling for us automatically. It knows when to wait for things to be available before it schedules something else, like this last call to add arrays. It's doing all this asynchronously over a cluster. And the other nice thing that it did for us is, if you recall the definition of add arrays, I was supposed to pass into NumPy arrays to that task, but instead I passed these references. And Ray automatically unpacks them for us and passes the actual objects down into the underlying function. So when you're sequencing stuff like this, you write code like you would normally write it if it were just all synchronous and Ray was involved. There are some obvious changes you can see here with .remote and so forth, but conceptually it's pretty straightforward what you have to write. And then Ray handles a lot of these details like scheduling these asynchronous computations in the right order, unpacking references and so forth when necessary. So it does a lot of nice stuff for you. Now, the one thing we haven't dealt with, though, is what if I need to distribute state? And a typical example in natural language processing is what if I'm distributing a model over a cluster and training shards of it at a time. That's obviously state I need to manage, and there's no mechanism so far that gives me an easy way to do that. Well, just as Ray leverages a familiar idea that we already know for tasks, namely functions, and turns those into tasks. It does the same thing for distributed state by leveraging something we already know, which is the idea of a class. We've used object-oriented classes forever to encapsulate some state and behavior in one little package. What we have here is a simple example of some sort of counter. It's initialized to 0, and every time I call it, it's going to increment that value, return the current value, and then I can do something else with it if I want. But this value, this count, is the actual state that I want to track. And to turn that into a distributed so-called actor, and I won't go into the reasons for that name. It's kind of a historical term for this. Well, again, I use the same annotation, ray.remote. The thing about actors, just a little detail about that is this implementation automatically handles thread safety. I don't have to worry about synchronizing access to this state. The messages are processed one at a time that are sent to it, namely, do an increment. And so I have something that works in a very intuitive way that handles a lot of the low-level details of concurrency. Now, one other thing you have to add with actors is if you want to actually just get the value in a normal Python class, you would just read self.value. You can't do that in an actor. You have to have an accessor method. So that's why I added this method here, just to illustrate the need for that. And we use it in a very similar way. We create one of these actors with .remote. We call the methods increment with .remote. And then it turns out if you look at the references and you can pass an array to ray.get, you'll get 1 and 2 back. Again, we started at 0, we called increment twice, and each of these references will hold the values at, after the call returned, which will be 1 and 2. Anyway, that's most of the API right there. There's a few other things that we could talk about, but for time's sake, I won't. Instead, I'll just mention that you may never actually use the Ray API. but people who are implementing systems that need lots of distributed computing can leverage that for you and then give you libraries to do things like hyperparameter tuning, distributed training, reinforcement learning. Ray RLib is probably the biggest of the libraries bundled with Ray, and there's even a new one for model serving. Okay, so this is a conference about natural language processing. Let's talk about Ray used in a couple of popular NLP toolkits, namely Hugging Face and spaCy. So Hugging Face has become popular recently, in particular for its transformers package. As I said earlier, and as you all know, NLP models are the world's biggest right now in terms of deep learning, and it's very, very expensive to train these things from scratch. But fortunately, we have this very powerful technique called transfer learning, where we start with a pre-trained model that has generally good qualities for general purpose natural language processing. We add a few more neural network layers to it, and then we train for several epochs, for some number of epochs, tailored for the particular application that we want. And that's a drastically reduced amount of computation that you or I might have to do in order to get a good model for our particular purposes. And hopefully, it's fairly straightforward. Well, there are some challenges with this, though, and that is that there's still some hyperparameters that we have to tune in order to, do this extra training. And I'll talk about a few specifics in just a second. And there's a couple of papers and other resources mentioned in the Transformers documentation about the challenges of avoiding local minima when you're doing training, and that sometimes, and these are kind of related, I think, you can end up with quite a variance in the results if you're not very careful about your choice of hyperparameters. And so it's really important to not just naively just do this transfer learning, but to think carefully about the hyperparameters that you're using. Well, one of the ways that they are solving this problem is using the Ray Tune library, which is the library for hyperparameter tuning. In particular, it does a lot of the boilerplate you would have to do yourself about scheduling distributed execution of these jobs, where you try different hyperparameters to see how they do. But it also builds in some of the state-of-the-art algorithms for optimizing that process, like Bayesian optimization and population-based training, which allow you to, with the same set of compute resources compared to like a naive grid search over hyperparameters, you can get better results, like 5% better in this particular example in this blog post, just using population-based training rather than a naive grid search. Briefly, what population-based training is, and there's a nice description of it in this blog post, but it's the idea that I might have several parallel runs with, each one is using a different set of hyperparameters. And if it appears that some of them are doing much better than others, then it will actually copy over, let's say, one example of what seems to be a good set of hyperparameters over top an existing set that's being used in one execution, tweak them a little bit in the same sort of sense of like genetic mutations, like it happens in a population, and then proceed to train from there so that you're kind of converging towards what appears to be a very robust set of parameters, hyperparameters, in the sort of evolutionary sense. Pretty cool algorithm, and as you can see from the numbers I'm quoting here, with the same compute resources, you can get better, significantly better results when you think about 5% is actually quite a good number. And they actually used in this blog post several different hyperparameter sets in various ways, but the main ones were things like the learning rate, the weight decay, the number of epochs of training, and the per GPU batch size. Ironically enough, they didn't actually look at like the number of extra network layers that you could add to the algorithm. I think that's because it's reasonably well established and good numbers for when you're doing transfer learning. So anyway, that's how Hugging Face is starting to use Ray, in particular Tune. The other one I'll talk about today is spaCy. There's a lot of overlap between these libraries. Actually, spaCy's transformer library wraps Hugging Face's transformers to integrate them into spaCy pipelines. What spaCy is actually doing in the release that's coming out soon, spaCy v3, is they're actually embedding the ability to use Ray to do distributed training. And this, right now, it's actually a separate project. If you go to the GitHub account for Explosion, which is the company that's behind spaCy, you'll see a spaCy Ray project. There actually is not a lot of source code in this. What they're really doing, actually on the next slide, I'll tell you what they're doing. Let me first describe just the small changes you would make in using it. If you use this Python command at the top to actually train a model with just spaCy by itself, in spaCy v3, you'll be able to add this subcommand spaCy Ray, and you'll now be able to say, I want to use n number of workers, whatever that n is, 2 in this case, and then it will do distributed training right off the bat for you without any real work on your part. You just get it for free, other than having to make the resources available. And they're also going to extend the use of Ray into some of the other aspects of the pipeline too in the future release. Like I said, the source code actually isn't very big. It's kind of a good reflection, I think, of the code quality in both spaCy and Ray. Mostly what it's doing is adding logic in the form of Ray actors and so forth to handle sharded parameters over a distributed cluster, where each of these actors will train on whatever shard it has locally for these parameters. It'll asynchronously receive updates from the other actors about how they've improved the parameters, merge those updates, and repeat this process. So there's a little bit of logic, some of which is a little complicated, although the lines of code is not that high to do all of this, but it's a pretty nice way of extending a powerful toolkit to be able to run over a cluster with relatively little effort. Well, other ways that you might use NLP, tokenization is a really good example where a lot of this can be done in parallel, where you don't have to be, shifting data back and forth, and other sort of data prep activities. I mentioned that spaCy is using Ray for distributed training, and we saw how Hugging Face is using Ray Tune, where you could also do this yourself with some of these libraries if you have some custom training algorithms that you use. Ray SGD is another library that's specifically designed to make it easier to run distributed TensorFlow and PyTorch training. And then finally, there's a library called Ray Serve that's a really lightweight, easy to use, but scalable library for model serving. It's not really an enterprise library in the sense of like traceability and model management and data governance and all that stuff. But if you need, relatively lightweight but easy to use tools for serving models, I would check it out. So a couple of weeks ago was Ray Summit. There were a bunch of talks actually from people involved in the Hugging Face and spaCy projects about how they're using it, as well as other talks about Ray. What I would do is, I'm not sure if the talk details are still up at raysummit.org, but you can find details on the Anyscale blog and also the Anyscale YouTube channel will have the videos. Once again, please check out Domino for all of your needs. And thank you very much for listening today. And here's some links where you can find more information. Also, feel free to reach out to me through email or Twitter.